All right, let's take a look at section 2.3, polynomial functions of higher degree with modeling. Okay, first let's talk about graphing transformations of monomial functions. An example of this in this is like example 1 in the book, but it's actually a different example. So same instructions, different problem, so that you can actually look at example 1 and try to figure out that one instead, and have just another tool for helping you understand this. The instructions say, describe how to transform the graph of an appropriate monomial function f of x equals a sub n of x time to the n. So we have some term a sub n that we have in front of x to some power into the graph of the given function. Sketch the transformed graph by hand and support your answer with a grapher. Compute the location of the y-intercept as a check on the transformed graph. Okay, so that's a whole lot of instructions. Let's break this down one at a time. First off, this g of x equals 2 times x minus 1 cubed. The monomial function that this has to do with is the cubic function. It's the shift and stretch of f of x equals x cubed. Okay, and that's important for us to realize, is what is the basically parent function of this. Then it wants us to describe the transformation that's being done to x cubed. Well, inside of here, this -1, because it's inside my parentheses, means I'm going right 1. So I'm shifting my graph of x cubed right 1. And then outside of my parentheses, this 2 means that I'm vertically stretching 2. Okay, so that is the description that they're looking for, is we're going right 1 and we're vertically stretching by a factor of 2 of the graph x cubed. And it wants us to sketch the transform graph by hand, and then after we've sketched by hand, look at what we did on an actual calculator or something that graphs. Okay, so if I want to sketch this by hand, this is just going to be kind of a rough sketch. But normally, one of the easy points to graph on a cubic function is the point 0, 0. And so this is where my shift is going to come in, is that my point is not at 0, 0, it's to the right 1 at 1. And then from there, I have my cubic function, which goes up to the right, down to the left, and it's vertically stretched too, so it needs to go up faster than normal, which is kind of hard to represent. So just do your best to kind of get that point across. What matters to me, and probably to most teachers, is more that you recognize the vertical stretch of 2 over here. Then whenever you sketch your graph, we know it's not going to be perfect. So try to make it look like you stretched it 2, but don't stress out about it. You can also use plugging in points to help you graph this if you want a more accurate graph. And if we were given a graph to put this on that had like grid lines and stuff, then we'd want to make it a much more accurate graph. It says to check it with a grapher, so I graphed this and then saved the image, and see, look, it looks like we did it right. We moved over 1 and then we drew our x cubed graph with a stretch of 2. When it says compute the location of the y-intercept as a check on the transform graph, if I plug a 0 in where x is, that gives me my y-intercept, so that I don't have to like actually compute this to try to find it. So 0 minus 1 is a -1. -1 cubed is still -1. And then -1 times 2 is -2. So our graph should be going through the y-axis at about -2. I got pretty close there. And then if we looked, our transform graph on our calculator looks like it goes through there. And obviously the graph on the calculator did it right. So it looks like we did a pretty good job there. So we talked about monomial functions. We've talked about stretches and shifts and things. So we're kind of putting this all together to say, if I have a monomial function, then I can think about what a normal graph would look like, and then just do shifts and stretches and shrinks. This is example 2 in the book. Graph the polynomial function, locate its extrema in zeros, and explain how it is related to the monomials from which it is built. So starting with A, if you put this in and graph it, you get something that looks like this, which looks pretty much like a normal cubic function. Okay, so our extrema are where we switch from increasing to decreasing or vice versa, and we end up with a maximum or a minimum. But if we look at that graph, I don't actually ever switch from increasing. I'm going up the entire time. So there's no extrema, no max or min. Then the zeros, well, it's going through at 0, 0. So my zeros are 0. And then it says, explain how it is related to the monomials from which it is built. So x cubed is a monomial and x is a monomial, and together they're giving us this polynomial, which with two terms, that really makes it a binomial. Okay, so it turns out that this x cubed graph close to the origin looks like the line y equals x. And that is what the connection to this is that I have almost a straight line here because this is plus x. Okay, so that may not make a little sense until we look at what this next one is. Hopefully this will make more sense. When I graph B, it ends up with a max and a min because this minus x is giving us the line negative x right here close to the origin. Sorry, that kind of looks awful. It gives us that negative x right there. Okay, so that means we have the x cubed function, but the minus x is basically giving us that behavior close to the origin. So that's kind of neat to look at. The local maximum, if we calculate it on our calculator by going to second trace, which is the calculate menu, and then picking maximum, we have the point negative 0.58 comma 0.38. We have a minimum of positive 0.58 comma, oh, that's not supposed to be there, negative 0.38. Okay, which makes sense that there's quite a bit of symmetry going on here because this is an odd function, and if you look at this, it looks symmetric about the origin. So that's why we have the same numbers just with different signs. The 0 on this one is also at 0. That's where it's going through the x-axis, is at 0. The next thing we're going to talk about is there's a theorem about local extrema and zeros of polynomial functions. Theorems are things that, as mathematicians, we can prove. And so someone somewhere, actually many people, many places probably have proved that this is true. So a polynomial function of degree n has at most n minus 1 local extrema and at most n zeros. So here's what this is talking about. If I have a cubic function, okay, that's a graph that goes through the origin, goes up to the right, down to the left. But we've seen other cubic functions that look very different from that. We've seen cubic functions that curve quite a bit. Okay, something that looks like that. This would have a max right there. It would have a min right here. And then it has 3 zeros. 0, 0, 0. Okay. The other kind of situation that we could have is we could have a graph where it ends up touching the x-axis and coming back down and then going back up. Okay, so this still has a max and a min, but only has 2 zeros because it just touches here and doesn't go through, and then there's my other 0. So what this is saying is that if I know it's a cubic function, I know it's the degree of 3, I have at most 2 extrema, a max and a min, and at most n zeros. So I can't have more than 3 zeros here. I can have less than 3, but I can't have more than 3. And I can't have more than 2 extrema, my maxes and my mins. And the same thing works with like a cubic function, not a cubic, a quartic function, which is when we have to the 4th power. Okay, our simplest quartic function, which is x to the 4th, it looks like a parabola that's just kind of bottomed out a little bit more. Something like this. So this has 1 extrema, it has a minimum, and it has 1 0, which is at 0, 0. Well, the craziest looking, well, not necessarily craziest, but a crazy looking, more crazy looking graph would be one where it does this, basically. It's not a completely accurate sketch, but you get the picture. Well, we have 3 local extrema. We have 1 max and 2 mins, and then we have 4 zeros. Okay, because the degree is 4, I can have at most 4 zeros. Not most, yeah, at most 4 zeros and at most 3 extrema. So that's what that theorem is talking about. I'm going to end part 1 right here. Maybe. There we go.